IP, or Internet Protocol, is the fundamental network layer protocol of the Internet. It defines the format and handling of datagrams, which are the basic units of data that include both the payload and the IP header. IP is connectionless, meaning it sends each datagram independently without establishing a session, and delivery is not guaranteed. It interacts with upper layer protocols like TCP and UDP using two primitives: send, which initiates delivery, and deliver, which passes incoming datagrams to the application. IP also handles datagram routing, determining how packets travel across networks, and performs error detection and notification, although not correction. Finally, IP enforces a lifetime limit via the time to live (TTL) field, ensuring that undelivered datagrams don't circulate indefinitely in the network. This diagram shows the structure of an IPv4 datagram header, which plays a key role in how packets are processed and routed in a network. At the top we have the version field, which is 4 for IPv4, and the header length, or HLEN, which tells us the length of the header in 32-bit units. Next are DSCP and ECN, which are used for quality of service and congestion notification. The total length field gives the entire size of the datagram, including both header and payload. We then get into the fields related to fragmentation. Identification tags fragments of the same original packet. Flags include two important bits: DF for don't fragment and MF for more fragments. And the fragment offset helps the receiver reassemble the data. This offset is measured in blocks of 8 bytes. The time to live, TTL, sets how long the datagram can stay in the network before being discarded, preventing infinite loops. The protocol field tells IP which upper layer protocol, like TCP or UDP, should handle the payload. The header checksum allows error detection on the IP header itself. We also see the source and destination IP addresses, which identify where the datagram is coming from and where it's going. Finally, there's room for options and padding, which can be used for alignment or special control features. The Internet Protocol allows each IP datagram to have a maximum size of 65,535 bytes, which includes both the header and the payload. This limit is determined by the 16-bit total length field in the IP header. The time to live, or TTL field, controls how long a datagram can remain in the network. While it's defined in terms of time, in practice it functions as a hop counter. Each router that forwards the packet decrements the TTL by 1. If the TTL reaches 0, the datagram is discarded to prevent it from circulating indefinitely due to routing loops. The maximum TTL value is 255, and in most cases it's used to represent the maximum number of hops the packet is allowed to traverse before being dropped. The Internet Control Message Protocol, or ICMP, is a vital part of the IP suite. It's not used to carry user data, but instead acts as a control protocol, helping routers and hosts exchange diagnostic and error information. ICMP is used for functions like reporting errors, checking if a host is reachable, or signaling that a router is overloaded. Interestingly, although ICMP operates at the network layer, it's actually carried inside IP datagrams. This creates a violation of the strict layering principle, because it means a network layer protocol depends on another network layer service to be transported. The diagram at the bottom shows ICMP sitting at the same layer as IP, but also highlights how it's transmitted within IP. ICMP, defined in RFC 792, is carried by IP and consists of two main types of messages: error reporting messages, destination unreachable, time exceeded, query messages, echo request, reply used in ping. The diagram illustrates how an ICMP message is encapsulated. At the lowest level, we have the data link layer, which wraps the IP packet. Inside the IP packet, the IP payload contains the actual ICMP message, which itself is made of an ICMP header and ICMP data. This encapsulation structure shows how ICMP piggybacks on IP. It's not a transport layer protocol like TCP or UDP, but it relies on IP to move across the network. ICMP messages fall into two primary categories: error reporting and query messages. For error reporting, ICMP's role is not to correct issues, but simply to signal that a problem occurred during the delivery of an IP datagram. When such an error is detected, ICMP sends a message back to the source of the original datagram, including the IP header and the first 8 bytes of the packet that caused the issue. Typical error messages include destination unreachable, type 3, indicating that the packet couldn't be delivered; source quench, type 4, now obsolete, which was once used to signal congestion. Redirect, type 5, suggesting a better route. Time exceeded, type 11, which shows up when a datagram's time to live expires, often observed in tools like TracerRoute. And parameter problem, type 12, which signals malformed headers or incorrect fields. The second group, ICMP query messages, are used to gather information or verify reachability. A common example is the echo request reply, types 8 and 0, which is the basis for the ping tool. Other examples include timestamp request reply, types 13 and 14, useful for time synchronization, and address mask request reply, types 17 and 18, which helps determine the subnet mask of a device. Some ICMP types, like router solicitation and advertisement, types 10 and 9, are used in more specialized network discovery scenarios. ICMP Type 3 messages are used when a router needs to notify a sender that a packet cannot be delivered. These are known as destination unreachable messages. When a router discards a packet due to an issue like a missing route or an unreachable host, it sends one of these messages back to the source. The message includes a type field set to 3 and a code field that identifies the specific reason. For example, code 0 signals that the network is unreachable. Code 1 means the host is unreachable, and code 2 refers to a protocol issue. Code 3 is used when a port is unreachable, while code 4 indicates that fragmentation is needed, but the don't fragment bit is set. Finally, code 5 is for cases where source routing fails, to help the sender identify the problematic packet. The ICMP message also includes the header and the first 64 bits of the original IP datagram. This context allows the sender to match the error with the exact flow or session that triggered it. ICMP Type 5 messages are used for redirection. They allow a router to inform a host that there's a better next hop available for reaching a specific destination. In other words, it helps optimize routing by correcting inefficient paths. In the example here, host B is trying to reach destination A. It sends the packet to router R3, assuming it's the right gateway. However, R3 realizes that router R2 is a better option to reach A. So R3 forwards the packet to R2, but also sends an ICMP redirect message back to B, advising it to use R2 directly in future transmissions. This redirection helps reduce unnecessary hops and improves routing efficiency by dynamically informing hosts of better gateways. However, it's important to note that redirect messages are only sent under strict conditions to avoid security risks or routing loops. ICMP Type 11 messages are used to report a time-exceeded condition. These are typically generated when a datagram fails to reach its destination due to a time-constraint violation. There are two cases where this happens. When the TTL field in the IP header reaches 0, routers will discard the packet and send an ICMP message with code 0 inches back to the original sender. This is useful for detecting routing loops or for applications like TracerRoute. Alternatively, if a datagram was fragmented and not all fragments arrive within a certain time window, the destination host will discard the partial data and send an ICMP Type 11 with code 1. This signals a timeout due to incomplete reassembly. In both cases, the ICMP message includes the IP header and the first 64 bits of the original datagram to help the sender identify the packet that triggered the error. ICMP Type 12 messages are used to report parameter problems in IP datagrams. These occur when a router or host encounters a field in the IP header that is either incorrectly set or not understood. When the code is 0, it indicates that there's an invalid value in a specific byte of the IP header. A pointer in the message will identify the exact byte where the issue was detected. This helps the sender debug or fix the packet generation logic. If the code is 1, the problem is that the packet included an option that's either not implemented or a required field is missing. In both cases, the packet is discarded and the ICMP message is sent back to the source. As with other ICMP error messages, the response includes the IP header and the first 64 bits of the offending datagram, which helps identify the original transmission. ICMP query messages are used not to signal errors, but to request information or perform network diagnostics. The most familiar example is the echo request and echo reply, types 8 and 0, used by tools like Ping to check whether a host is reachable and how long it takes for packets to travel back and forth. Other query types include the timestamp request and reply, types 13 and 14, which measure the time it takes for a datagram to travel across the network, useful for synchronization or measuring one-way delay. The address mask request and reply, types 17 and 18, allow a host to discover the subnet mask being used on its local network. Finally, the router solicitation and advertisement messages, types 10 and 9, are used by hosts to discover routers on the network. These are especially useful in dynamic IP environments, where routing configuration needs to be discovered automatically. Echo request and echo reply messages identified as type 8 and type 0 in ICMP are used to check whether a host or router is reachable. In this diagram, host A sends an echo request toward host B, which travels across multiple networks and routers. If B is up and reachable, it sends back an echo reply. This mechanism is the foundation of the ping utility, widely used for network diagnostics. If the echo reply returns, we know the end-to-end path is working. If not, it suggests a problem somewhere along the route, either a network failure, a down host, or a filtering device blocking the traffic. Traceroute is a tool that uses ICMP echo request and reply messages along with the time to live field in the IP header to discover the path to a destination host. It works by sending an echo request with a TTL of 1. The first router, R1, decrements TTL to 0 and drops the packet, replying with a time exceeded message. Then a second echo request is sent with a TTL of 2. The second router, R2, drops the packet and sends back the same error. This process continues, increasing the TTL by 1 each time until the packet reaches the final destination, which then responds with an echo reply. In the diagram, host A sends 3 echo requests with increasing TTL values. The responses from routers and the final server allow A to learn the full path taken through the network. Traceroute reveals the sequence of router IPs that are forwarding packets to the destination. ICMP timestamp request and reply messages, identified as types 13 and 14, are used to measure network timing and delay. When the source sends a timestamp request, it fills in the originate timestamp with the current time. As soon as the destination receives the message, it fills the receive timestamp, and just before sending the reply, it fills the transmit timestamp. This allows the sender to calculate the round-trip time and clock offset between the two nodes. It's a useful tool for time synchronization and delay measurement in networks. ICMP messages of type 17 and 18 are used for address mask request and reply. These messages help a host or router determine the subnet mask of the local network. The source sends a request and the destination responds with the correct address mask value filled in the corresponding field. This was especially useful in early IP networks where subnet configuration might not be explicitly known by the sender. The message format includes type, code, checksum, an identifier, sequence number, and finally, the address mask.